Universe, cosmic architecture on the largest scale. To understand how this architecture came about, its details must first be firmly established by constructing maps to show in what direction the galaxies lie and how far off.
So the aim is to measure the distribution of galaxies on large scales in the universe, and this is done in two stages. Firstly, large glass photographs are taken on a telescope in Australia, the Schmidt telescope, and then those photographs are scanned here by a laser-controlled plate measuring machine. The aim of this first stage is to measure the positions precisely on the sky of galaxies, and also to tell the difference between those galaxies and the stars in our own Milky Way galaxy. Now, to tell the difference between a star and a galaxy, here we've got a very small section of the photographic plate as scanned by this APM machine. And this is just an area that's 4 millimeters on the plate, very small fraction of the data that's on this photographic plate. And here we see a few galaxies and stars. A galaxy image is, of course, rather fuzzy and faint, has a low surface brightness, whereas a star in our own galaxy is very sharp, round, and has a bright core. And it's this essential difference between the images that allows the computer automatically to tell the difference between a star and a galaxy. A catalogue is then made up of all the faint galaxies down to some fixed brightness limit, and this is then taken by the astronomer to a larger telescope in order to measure the spectrum of the light from each of these galaxies to determine its redshift. The redshift is that essential third dimension in the position of a galaxy in space. So it's a two-stage procedure. The first stage is to measure the plates. This gives us the two-dimensional positions of the galaxies on the sky. And then the second stage is to measure the redshift of the galaxy with a larger telescope. And this gives us the valuable third dimension. Now, we shouldn't underestimate the size of the task. And just to illustrate that, I'll show you here the amount of data that comes from these plates when they're scanned by this APM machine. This rack of magnetic tapes represents all of the digital data that is recorded from the plates in the southern hemisphere. You can see it really is a large amount of data. But the ultimate goal is very worthwhile because understanding the spatial distribution of galaxies in the universe is a very important cosmological question. Let's just go and have a look now at some of the scientific results. So each of these areas has been scanned by the APM plate measuring machine, and so the distribution of galaxies in two dimensions has been built up, ready for measuring the distances with the spectrographs on the larger telescopes. Now, for bright galaxies, their numbers on the sky are sufficiently small that one measures them one by one with the large telescopes and slowly builds up a three-dimensional map of the distribution of galaxies in the local universe. And here is one of those such maps, and it represents a sort of wedge diagram where the observer is at the apex of the wedge, and as you go out, you're measuring to larger and larger distances with the angle across the wedge itself. And you can see that the distribution of galaxies is highly non-random. There are large clumps, clusters of galaxies on scales of 1 megaparsec or so, superclusters on scales of 10 megaparsecs, 20 megaparsecs, and even bridges and sheets joining these clusters on scales much larger. One of the most surprising results that has come out of the very nearby redshift surveys was the discovery of the Great Wall, a huge chain of galaxies about 100 megaparsecs long, which is one of the largest structures in the local universe. Now, astronomers are very concerned about these kind of structures, how they grew and formed in the early universe, but also whether the universe is really homogeneous on large scales. After all, this is a fundamental question in modern cosmology. In order to check that, we need to go to even larger scales and survey the universe in larger volumes still. Now here, a new instrumental technique makes measuring the redshifts much easier. By going to very large distances, we see many more galaxies, of course, and so their surface density on the sky is very much higher. Then we can use a fiber optic technique, where the light of each faint galaxy is fed by an optical fiber into the spectrograph, enabling us to measure the redshifts of galaxies, not one at a time, but 50 or 100 times simultaneously. This means that, of course, we can measure redshifts much quicker than we would otherwise be able to do. Now, the results that come out of these fiber optic surveys, which are essentially a very deep pencil beam in space, sort of like a borehole into the deep universe, are shown on this diagram here. And here one is looking at the distribution of galaxies in a single one-dimensional line. This is what one would expect if galaxies were distributed uniformly, and you can see the distribution isn't anything like that. It's very, very clustered and spiky. And fortunately, one of these spikes goes right through this Great Wall, and so one is in a sense intersecting wall after wall in making these deep pencil beam surveys. This was a very surprising result. Although we knew of the existence of the Great Wall, we didn't know how many such structures there might be in the universe. In fact, it appears that they're very common. Now, it's this complementary picture here between the local surveys, which cover a wide panoramic angle, but perforce have to study the galaxies one by one, and the deep pencil beam surveys here, which show the distribution of galaxies along a single line, that give us our picture of the current distribution of galaxies. In the future, what we would like to do is, of course, to open up the panoramic angle and go deep, and that's where the new telescopes, which will simultaneously have a wide field of view and have this fibre optic gain, will enable us to get the best picture of the distribution of galaxies in the deep universe.
These three-dimensional surveys are obviously the ultimate goal, but they are going to take a long time to complete. Fortunately, a good deal can be learned from two-dimensional surveys, directions without distances.
Although three-dimensional surveys have given us a good visual impression of what structure in the universe looks like, there is in fact much more data in two dimensions. We have surveys of several million galaxies, in fact, whereas only 30,000 galaxies have measured redshifts. So we can get much more accurate results from two-dimensional surveys. The results show that galaxies are clustered out to scales of about 100 megaparsecs. On larger scales, the universe is very nearly homogeneous.
How do astronomers explain this large-scale distribution of galaxies? First, they have to understand how the galaxies themselves form.
Understanding the formation of galaxies is one of the biggest problems in modern cosmology. We believe that the universe started off from a hot, dense initial state. Shortly after the Big Bang, small irregularities were generated by exotic physical processes, and these grew under the action of gravity to make the structure that we see in the universe today. Now, can we deduce, by looking at observations, what the starting conditions in the universe were like? I can illustrate this by looking at computer simulations. Here is a simulation of a slice of the universe. It is 300 megaparsecs by 300 megaparsecs by 30 megaparsecs deep, and shows that galaxies are clustered strongly on large scales. We see filaments, bubbles, and voids. Here is the simulation at an earlier time, when the universe was only 15% of its present age. The structure is less pronounced, and shows how gravity amplifies small irregularities to form galaxies, clusters of galaxies, and superclusters. I've run lots of simulations like this, and it's interesting to ask whether we can tell the differences between different theoretical models. This isn't easy, as illustrated by these two models. On one side, I have a computer simulation which is designed to reproduce what we see in the real universe. On the other side, I have a simulation of the cold dark matter model. The two models are rather similar, and in fact we have to apply rather complicated statistical analyses to distinguish between them. In fact, the results fit in quite well with models with cold dark matter, but to make a precise match with the observations, some extra ingredient is required. So cold dark matter with perhaps a trace of hot dark matter in the form of massive neutrinos provides a good match to the observations. Another possibility is to have a cosmological constant from Einstein's theory of general relativity, and together with cold dark matter we can make models which work. To distinguish between those models requires more difficult and complicated observations. For example, looking at the motions between galaxies or looking at the anisotropies in the microwave background.
Exciting new intellectual territory is opening up here. Einstein's theory of general relativity and the microwave background radiation. These concepts are so important that much of the next block of this course is devoted to them. By the end of this final block, you will appreciate more fully how the large-scale distribution of the galaxies can be explained.